Hello, my name is Peter, and this is my submission for the Summer of Math Exposition. In Precalculus, there's a formula used to find the roots of complex numbers. You take the complex number and convert it into its polar form, and then you plug the r and theta into this formula, which will spit out the roots. This is called the nth complex root theorem. I think that the way that this concept is taught does not give justice to the underlying geometric beauty of the complex roots, and it is also highly forgettable. I hope that by the end of this video you will have a more intuitive understanding about complex roots and will be able to appreciate the geometric beauty as well. Before we get to the complex plane, I want to start on a Cartesian plane. Let's take some point, say 2, 3, and rotate it 90 degrees counterclockwise. This yields the point -3, 2. As you may notice, the 2 and the 3 have switched places and the 3 has become negative. This can be generalized as when a point A, B is rotated 90 degrees counterclockwise, the resulting point is -B, A. In the imaginary plane, there is a similar operation. Just as a quick recap, in the imaginary plane, the x values are ordinary numbers and the y values are imaginary numbers. Also, points more commonly are expressed as position vectors, so coordinates take the form of x plus yi instead of x, y. Now, if we take some point 2 plus 3i and multiply it by I, then we get the point -3 plus 2i. Notice anything similar? We see that multiplying a complex point by I has the same effect of rotating that point 90 degrees counterclockwise. More generally, we can say, multiplying by complex numbers has a property of rotation. What if we wanted to rotate a complex point by, say, 45 degrees? What complex number will we have to multiply by then? Well, if we start with a complex point, 1 plus 0i, or just 1, and rotate it by 45 degrees, then that would result in the complex point cosine of 45 plus I sine of 45. This makes sense using the unit circle, but also makes sense geometrically. If we use the position of the resulting point to make a right triangle with hypotenuse length 1 and base angle 45, then we know that the x component or real component would be length cosine of 45, and the y component or imaginary component would be sine of 45. Remember, we wanted to find a complex number that when multiplied by would rotate another complex number by 45 degrees. So we should ask what number, when multiplied with 1 plus 0i, would result in cosine of 45 plus I sine of 45. And that number is cosine of 45 plus I sine of 45. To show that this works, let's rotate 3 plus 2i by 45 degrees. To do this, we have to multiply the two complex numbers. After simplifying, we're left with a new complex point. And if we graph the 2 points, then we indeed see that it is 3 plus 2i rotated by 45 degrees. This can be generalized as, if you want to rotate a complex point by some angle theta, then multiply that complex number by cosine of theta plus I sine of theta. An important property of this rotation formula, let's call it cis of theta, is that cis of a plus b equals cis of a times cis of b. For example, if you wanted to rotate a complex number by, say, 105 degrees, you could either use the rotation formula for 105, or you could break 105 into nicer trig numbers, let's say 45 and 60. And then first rotate by 45 degrees, and then by 60 degrees. These two operations are geometrically equivalent, and so we can set them equal to each other. With a little bit of manipulation, we get back to that original property that cis of a plus b is equal to cis of a times cis of b. This property has implications when it comes to exponents. For example, if you square the rotation formula, it is the equivalent as doing the rotation twice. In other words, cis of theta squared is equal to cis of 2 theta. Say we wanted to find the complex values of x that satisfy the following. X squared equals negative 1. Looking at the equation x squared equals negative 1, you could arrange it to x equals square root of negative 1, which is I, one of the answers. Another answer would be negative I, which is negative 1 times I. Because 1 squared, the negative 1 turns into a 1, and the I squared becomes negative 1. The algebraic approach is valid, but when trying harder complex equations like x squared equals 3 plus 4i, it would end up becoming a lot more guess and check. This is where the geometric approach may be more helpful. If we think about it, x squared is really just x times x, and negative 1 is a complex number, negative 1 plus 0i. Remember, multiplying by complex numbers has the property of rotating. So, x times x equals negative 1 plus 0i is like asking, if you rotate the vector 1 twice by 7 degrees theta, then what would theta have to be for the resulting vector to be negative 1 plus 0i? In this case, we clearly see that 90 degrees is one of the answers. The second answer is harder to spot, but if you rotate 270 degrees twice, then you end up rotating 540 degrees, which is going 1.5 times around, or the equivalent of 180 degrees. Again, going from 1 to negative 1. If we plug in 90 and 270 into the rotation formula, then we end up with cosine of 90 plus I sine of 90, which is I, and cosine of 270 plus I sine of 270, which is negative I. The same answers that we got algebraically. Let's try one more example before we get into the formula. Say we wanted to find all of the fourth roots of the complex number in negative 1/2 plus I times root 3 over 2. If you want, pause the video and try it yourself. Okay, starting with the solution. First, we can rearrange the equation a bit, and then using tangent, we can convert the complex number into its polar form. From this, we see what we are being asked. What angle, when rotated 4 times, would end at 120 degrees? One of the answers is relatively simple, 30 degrees. The other ones are a bit harder to spot, but there's one at 120 degrees. There's one at 210 degrees. And the last one is at 300 degrees. To get the actual complex roots, you can take the degree values and plug them into the rotation formula. A pattern you may see is that all of the roots are evenly spaced on the circle, and it makes sense that they are split by 90 degrees, because when you rotate 90 degrees 4 times, it results in 360, a full circle, having no effect on the end location. Take 210 for an example. It can be seen as 30 plus 90 plus 90, which when rotated 4 times becomes 120 plus 360 plus 360. The 360s go away because they're full circles and have no effect on the end location, and so you're left with 120, our desired outcome. Now let's take a look at the theorem. Remember, the nth complex root theorem tries to find the complex root of complex numbers. Geometrically, this is like asking, what complex number, when multiplied by itself n times, will yield the complex number you're taking the root of? First, let's look at the bracketed part. This should look familiar, like the rotation formula, which it essentially is. Now let's take a look at the angle being plugged into the rotation formula. A quick look at variables. N is the root that you're taking, theta is the desired n angle, and k is the integer values from 0 to n minus 1. Let's start by plugging in 0 for k. After simplifying, we get theta over n, which is our first solution. If we want to land on theta degrees after n rotations of the same amount, then you would want to rotate by theta over n times. Something to note here is that theta is in radians and not degrees. Now let's focus on the second term. We can rearrange a bit and we end up with 2 pi over n times k. 2 pi in radians is a full rotation around the circle, so divided by n makes it 1/n of the circle. K ranges from 0 to n minus 1. This term is essentially showing that all of the complex roots are spaced out by 2 pi over n radians. This matches up with the observed pattern in the problem before. When this term is multiplied by n, this simplifies to k times 2 pi, and because k is always an integer, it will always be some multiple of 2 pi, or a full circle, having no effect. Putting the two terms together, you get one term that when multiplied by n results in a rotation of theta, and another term that when multiplied by n results in an integer multiple of 2 pi, which has no geometric effect, but algebraically produces a different complex number when placed into the theorem. Lastly, let's look at the part outside of the bracket. In all the examples today, the complex numbers had a radius or a length of 1, but that might not always be true. This term out front just makes sure that the radius of the roots is correct. In the beginning, we started with a very complex theorem, but in essence, all it is doing is finding all the angles that when rotated n times will land on the complex number that you're taking the root of. There are a couple people I'd like to thank. First of all, the viewers, thank you for watching this far. I'd also like to thank Math with Bad Drawings by Ben Orlin for the inspiration. 3 Blue 1 Brown's video on complex numbers, which I would highly suggest watching. Link is in the description. Precalculus by Sullivan and Sullivan. The Manim Community, and my friend Hojin Liu, who helped with content editing.